Le Chatelier's principle. So it is based on fundamentals of stable equilibrium. What actually Le Chatter's principle says, it states that when a system is at equilibrium and is subjected to change in pressure, concentrations, temperature of a reacting species, the equilibrium states get disturbed. So equilibrium shift to such a direction so that it undo the changes. So Le Chatter's principle simply says that when a system is at equilibrium and when we are actually disturbing the equilibrium states by changing the pressure, temperature or concentrations of the reacting species, means the reactants or product concentrations, if you changing, then the equilibrium of that states get disturbed, and what equilibrium will do, it shift in such a direction so that it undo the changes. It is actually, we can explain that if this is the stable state of this ball, so this is the, in this place this ball is fully stable, and suppose what I do, I just pause it and I will move these balls to here. Then what happened, this ball will come again and this will go little here. After that again this will decreases its positions, and finally this ball always stay in this position. This is the stable position of the ball. So if you move the ball towards like red, towards the red, that ball has moved to this positions, then again this position of the ball is not stable, so this ball again will go here little, and after at the last time it always stay in this position, in the green ball position. So this green ball position, I will write this blue position of the ball is the stable position of this ball, so it always try to stay in the stable, in the blue position of the ball. So equilibrium is the same, like if you disturb the equilibrium always wants the equilibrium at achieved means on that position, that is stable, and if you suppose subjected to changes the reacting species, like this ball, if you change little bit, if you move this, then it will go to red side, red sign position of the ball, and again it will come here. After that, finally it will come here. So like that, if you change the reactant species, that is concentration of reactants or concentration of the product, then what will happen? The equilibrium try to unchange that changes and wants to come to that stable positions of where the reactions is stable. Okay, so that's what the Lee-Chatter's principle says. So equilibrium can be disturbed. Actually, we are disturbing the reactant species, that is concentration of reactants or concentration of products. We are actually increasing or decreasing, or we are adding some inert gases. So if you add something to the reactant species, that is concentrations of reactants on a product, then equilibrium of that reactions will disturb. So there are 4 to 5 methods or many methods by which equilibrium get disturbed. So equilibrium can be disturbed first change in concentrations of reactants or products. So what happens? Suppose this is A gas plus B gas is going to change C of gas plus D of gas, and if the reactant concentration is increases, if reactant concentration increases, then the equilibrium state, suppose this reaction is at equilibrium, and if you increase the concentration of reactants, then the equilibrium of these reactions get disturbed, and the equilibrium do not want this disturbance. So if you increase the reactants, then equilibrium wants to decrease the reactants so that equilibrium will not disturb. So what we will do? Equilibrium, if concentration of reactants increases, then equilibrium wants to decrease the concentration of reactant. So for decreasing, it will shift forward directions. So if reactants is used in a reaction, then reactants will decrease. So how, where it is using? If reactions will go forward, then concentration of reactants will decrease. So if you increase the concentration of reactants, then equilibrium will get disturbed, and equilibrium do not want to change this, they do not want to change this disturbance, so it will try to decrease the concentration of reactants. So for decreasing the concentration of reactants, it will shift forward directions. So forward shift occur, and if you decrease the concentration of reactants, suppose if you decrease the concentration of B, then what happens? The reactants do not want this decrease. So always equilibrium do not want any changes in a reaction. So if you decrease the concentration of reactants, suppose B, then equilibrium wants to increase the concentration of B. So for increasing the concentration of B, it has to shift backward directions. So if you decrease the concentration of reactants, then backward shift occur. Similarly, if you increase the concentration of product, suppose concentration of D, if you increase, then equilibrium do not want this change. So what? So how it will decrease the concentration of D, that is product, by shifting backward directions. So backward shift occur. Similarly, if you increase, this is I increase, if you decrease the concentrations of product, so if concentration of product is decreasing, suppose concentration of D we are decreasing, then what happens? Equilibrium do not want this change, so it wants to increase the concentration of product, so that whatever it decreases, that will be counterbalance. So for that, what it will do, a forward shift will do. It will use reactants and wants to make product, so that the what amount of product has decreased, that will be come again. So it will shift forward. So forward shift occur. So what says, suppose A gas plus B of gas is C of gas plus D of gas. So if you increase the concentration of reactants, then then forward shifts occur. So in Haber process, that is N2 what happens here? So in Haber process, what they are doing, ammonia is easily liquefy in water, because due to hydrogen bonding and the chemical nature of ammonia, the ammonia easily get liquefied in water, whereas the nitrogen and hydrogen gas not easily able to liquefy as compared to nitrogen. Nitrogen is more easily liquefied. So what they are doing, they are actually liquefying the nitrogen gas. So if they liquefy the nitrogen gas, then concentration of product is decreasing. By liquefying, the concentration of product is decreasing. So if concentration of product is decreases, then the equilibrium do not want this change. So what the equilibrium will do? It will do forward shift, so that what amount of ammonia is lost by liquefy, that again converted. So in Haber process, what they are doing, they continuously removing the concentrations of ammonia by doing liquefying, and adding continuously concentrations of nitrogens and concentrations of hydrogen. So they continuously adding the nitrogen hydrogen gas, and at the same times they removing or liquefying the ammonia, so that more and more amount of ammonia they are synthesizing. So in Haber process, so if concentrations of reactants is increases, reactants concentration increases, then forward shift occur. So they are increasing the concentration of nitrogen and hydrogen continuously. So continuously forward shift is occurring, and if concentration of product is decreases, then also forward shift occur. If it will decreases, then for counterbalancing, for again getting this ammonia, the forward shift has to be done. So by increasing the concentration of reactants and by decreasing the concentration of product, they are actually preparing more amount of ammonia. So this is the Haber process. Now in Haber process, Lee-Chatelier principles they are using, and they synthesizing the ammonia. So that is Haber process. So they are increasing the concentration of reactants. So if the concentration of reactants increases, then forward shifts occur, and concentration of product decreases, then also forward shift occurs. So by using this process, they are synthesizing ammonia. So next is change in pressure. So change in pressure of the reacting species. So this way also we can disturb the equilibrium. So how? If we increase the pressure, then equilibrium will disturbed. Equilibrium get disturbed, and wants to undo this by decreasing pressure. So if you increase the pressure, then equilibrium wants to decrease the pressure. So how it will decrease the pressure? So for that, we should know the ideal gas equation, that is PV and RT, ideal gas equations. But this relation says PV equal to N by V RT. So if we are increasing the pressure, and PV is inversely proportional to volume. If If we increasing the pressure, then volume is decreasing at the same times, because these are inversely proportional. If pressure increases, then volume decreases. And R and T are constant here. R and T are constant. So if pressure increases, then N by B, this whole terms has to increases, because R and T is constant and pressure increases. Therefore, to make this equations, N and B has to be increases. So if pressure increases, then N by B is increasing, means number of moles increasing. So how it will decrease the, so if pressure increases, then equilibrium wants to decrease the pressure. So how it will decreases? So if number of moles is increases, then equilibrium it will shift to less number of moles. So if equilibrium shift towards less number of moles, if equilibrium will shift towards less number of moles, then pressure decreases, because if pressure increases, then number of moles is increasing. So equilibrium do not want this increase of pressure. So what the equilibrium will do? It will do in such a way that pressure will decreases. So it will shift the reactions towards less number of moles where pressure is decreases. If pressure decreases, then we can say N by B RT. Here B is increasing, because P is inversely proportional by B. And if P decreases, the N by B whole terms, this has to be increases, because this is the constant. So P decreases, then N by B has to be decreases, means number of moles decreases, or less number of moles. So if we increase the pressure, then number of moles increases, and equilibrium wants to decrease the pressure. So equilibrium shift less number of moles. Equilibrium shift, you can write, towards less number of moles. So if pressure increases, and if we shift towards more number of moles, then on that side only pressure is increasing, but equilibrium wants to decrease the pressure. So for that, equilibrium will shift towards less number of moles. If equilibrium also shift towards more number of moles, then on that side again pressure is increasing. So equilibrium wants to decrease the pressure. So if we increase the pressure, then equilibrium do not want this change, so it wants to decrease the pressure. So how it will decreases? So if pressure increases, the number of moles also increasing. So it should do where pressure will decreases. For that, it will shift towards less number of moles. So we can say, if pressure increases, then equilibrium shift towards less number of moles. So pressure is directly, pressure is fully depend on number of moles. Let us say, suppose this is A gas plus B of gas going to give C gas plus D of gas. Here if you say delta Ng is number of moles in product, that is gas, minus number of moles, number of gas molecules, you can say number of, I will write number of gas molecules, number of gas molecules in product minus number of moles in reactants. Number of moles, not number of moles in reactants minus number of moles in product divided by number of moles in reactants. So see, so here delta Ng, towards product side how many moles? This is 1, this is 1, so 2 moles, and from reactant side here also 1, 1, so 2 moles. So delta Ng is 0. So if delta Ng is 0, then if you increase the pressure, then equilibrium should shift towards less number of moles to decrease its pressure. To decrease the pressure, equilibrium should shift less number of moles. But here, both product side and both reactant side and product side number of moles is same. Here is 2. Here is also 1 plus 1 is 2. So both reactants, both product side and both reactant side number of moles is same. So where equilibrium will shift? So for this type of reactions, if number of moles in both product side and reactant sides are same, then if you increase pressure or decrease pressure, there will be no effect. Example, if you say H2 gas plus I2 gas to HI gas, here delta Ng is 0. So here product side 2, reactant side also 2. So delta Ng is 0. For that gas, for this case, if you increase pressure or if you decrease pressure, there will be no effect. There will be no effect for this type of reactions. And if delta Ng is greater than 0, like we say A gas plus B gas plus 2 B gas. So here delta Ng is, so product side how many? 3 moles, reactant side 2 moles. So delta Ng is equal to 1. So for this case, if pressure is increases, then it should shift towards less number of moles to decrease its pressure. So equilibrium should shift towards less number of moles. So where less number of moles is there? In the reactant side. So here reactant side 2 moles, product side 3 moles. So less number of moles is present in reactant side. So if P increases, then for this case backward shift occur. Say the example, PCl5. All decomposition reactions like PCl3 gas plus Cl2 gas. Here delta Ng, product side 2, reactant side 1. So delta Ng is 1. So if you increase pressures for these reactions, then equilibrium will shift backward directions, because in backward only 1 mole is there and in forward 2 moles is there, so backward reaction. So for this type of reactions we used very low pressure, because if you increase the pressure it will go backward directions, and if you want to decompose PCl5 into PCl3 and Cl2 we have to do very low pressure so that it will do forward shift. Yes. Another type where delta Ng less than 0, like A gas plus 2B gas, C gas plus D of gas. Here you see delta Ng for product that is 2, reactant that is 3. So this is -1. So delta Ng is less than 0. So for this type of reactions, if you increase the pressure, then it should shift where less number of moles is there. So here 3 moles, here 1 plus 1, 2 moles. So if you increase the pressure, then less number of side should shift. So less number of moles is present in product side. So forward shift occur. So if we say the example, that is Haber process. We can say the Haber process or combustion reactions. In this combustion reactions, here you see here is 3 plus 1, 4 moles. Here 2 moles. So delta Ng, you know, that is product moles, that is 2, reactant moles, that is 4, that is -2. So less number of moles is there in reactant, in product sides. So if you increase the pressure, then equilibrium should shift less number of moles, and less number of moles is present in product side. So forward shift occur. So in this type of Haber process or in the combustion reactions, high pressure reactions are done at high pressure. So we understand that. The next is after that we will discuss volume. So effect of volume, how equilibrium get disturbing. So if we increase the volume, A gas plus B gas to C gas plus D gas. So if you increase the volume, then equilibrium will disturb, and equilibrium wants to decrease the volume. So how it will decrease the volume? So for that, you know that PB equal to nRT, ideal gas equations. So P equal to N by B RT, and if volume is increasing, then pressure will decreases, because pressure and volume are indirectly proportional. So if volume is increasing, then pressure is decreasing, and R and T is constant. So if pressure is increasing, then N by B concentration also should decreases, because R and T are constant. So to counterbalance of decreasing pressures, N by B whole term should decreases. So N by B decreases means number of moles decreases, but number of moles decreases. So if volume increase, so if pressure decreasing, if volume is increasing, then number of moles decreasing. So number of moles decreases means, but volume wants to decrease its volume, so for that it should shift more number of towards more number of moles. So if volume increases, then equilibrium wants to decrease the volume. For that but actual volume increases, then pressure is decreasing, and if pressure is decreasing, then number of moles or we can say easily, volume is decreases, then pressure is increases, and if pressure is decreasing, volume increases, then pressure is decreases, and if pressure decreases, then equilibrium should shift more number of moles, because pressure and volume are indirectly proportional. So for pressure case, we studied that if pressure increases, then equilibrium shifting is less number of moles. Equilibrium is shifting. So if volume is increasing, and pressure and volume are indirectly proportional, so if volume increases, then it should shift more number of moles. So if volume increases, then equilibrium wants to decrease volumes. For that, equilibrium should shift towards more number of moles. So for this case also, we can stay gas. So volume also depends on number of moles. So if volume depends number of moles, here also we have to study delta Ng equal to 0, and if delta Ng is greater than 0, and if delta Ng less than 0. So if delta Ng is 0, then actually if volume increases, then it is shifting towards more number of moles. But if number of moles is same, then there will be no effect. And if delta Ng is less than 0, delta Ng is less than 0, on that case, what we can say, suppose A gas plus B of gas going to give C gas plus D of gas. Suppose this is 2C gas. So here delta Ng is 3 minus 2, that is equal to 1. So delta Ng is greater than 0. So for this case, if volume increases, then it should shift more number of moles at equilibrium should shift towards more number of moles. So more number of moles is where present towards forward direction. So forward shift occur, and if volume decreases, then equilibrium will shift towards less number of moles. So for this case, if volume decreases, then volume increases, then it will shift towards more number of moles, and if volume decreases, then less number of moles, that is backward shift. So similarly, as we explained for pressures, we can also take examples, like if you increasing the pressures, then for higher pressures what will happen, and for combustion reactions what will happen, or for decomposition reactions what will happen. So the same way we can explain as we explain for pressures. So next terms we studied, that is adding inert gas. Adding inert gas at constant volume. At constant volume, if we add inert gas to equilibrium states, then what happens? Actually, inert gas means inert gas do not affect the number of moles, affect the number of moles, but it increase the volume. So if we are adding, so at constant volume, it say at constant volume, if we adding inert gas, there will be no effect. Why? Because we already said the constant is volume is constant, and inert gas only helps to increase the volume, but we assume that volume is constant. So inert gas is no effect for increasing our number of moles. So there will be no effect as we consider the volume is constant. So if at constant pressure, if you are adding the inert gas, then what happened? Inert gas only helps to increase the volume. So volume is increases. So if volume increases, then we already explained that it will shift more number of moles. Equilibrium shift towards more number of moles. So we already explained the effect of increasing volumes and decreasing volumes. So this is the same as the effect of increasing volume. So there also volume is increasing. So adding inert gas, we only able to increase the volume. So we cannot do any changes to number of moles. So it is same as volume. So whatever the effect is happening with volume, the same effect will happen if you if you add the inert gas. So pressure, volume, adding inert gas, basically volume and inert gas is same, because inert gas also helps to increase volume. So these three terms depends on number of moles. So if delta Ng of a reaction, delta Ng is 0, then if you increase pressure or decrease pressure, or if you increase volume or decreasing volume, or if you add inert gas, there will be no effect, because there will be, if delta Ng 0 means number of moles in both product and reactants are same. So if number of moles are same, then if you add pressure or volume or adding inert gas, there will be no effect, because these three terms depend on number of moles. So it will shift, like pressure is decreasing, then it will shifting towards more number of moles. If volume increasing, it is shifting towards more number of moles. So if moles are same in the reactions, then if you add or decrease volume or pressure, there will be no effect. So like A gas plus B gas, C gas plus D gas, here delta Ng is 0. So for this type of reactions, there is no rule of adding inert gas, increase or decrease volume, increase or decrease pressure. So there is these three things no effect if delta Ng is 0. And if delta Ng is not 0, not equal to 0, then we know that pressure, if it increases, then less number of moles, equilibrium shift. And if your volume increases, then more number of moles, equilibrium shifts. And volume and inert gas are same, because inert gas also only helps to increase the volume. So these things we have to remember. And fifth is adding temperature, and say increasing temperature or decreasing temperature. So if you increase the temperature in a reactions, in equilibrium state of a reactions, then equilibrium wants to decrease the temperature. So what it says, suppose A gas plus B gas is going to give to C gas plus D gas. Here increasing means, suppose I add here the heat. So if you, so in this side heat is coming extra, so equilibrium do not want this heat. So what will do, this reaction use this heat and wants to shift this directions. So this backwards direction it want to shift by using this heat, so it wants to decrease this heat, so it will shift backward directions. Like endothermic reactions, A gas plus B of gas, and if heat is given, then C of gas plus D of gas, forward shifts occur, because endothermic reactions this heat it will be used, and actually if we adding this heat, and equilibrium do not want this heat, and equilibrium wants to decrease this heat. So how it will decrease? By consuming this heat, and by consuming this shift it will shift forward direction, so forward shifts occur. Similarly for exothermic reactions, like A gas plus B of gas, C of gas plus D of gas. So exothermic means delta H is negative, so heat is releasing. So here suppose I say heat, so equilibrium do not want this heat, so it wants to shift backward directions, it want to use this heat and want to go backward directions. So for exothermic reactions what is occurring? Backward shifts occur. So summary of Le-Chatelier's principle, what I said, that pressure, equilibrium get disturbed by adding or increasing of these pipe these pipe cases mainly, like one if you concentrations. So if you increase or decreasing concentrations, then equilibrium will shift where concentration is decreasing. So if and like I already explained that if concentrations, so it depends on concentration. Suppose if you increase the concentration of reactants, then it will shift forward directions, and if you decrease the concentration of reactants, then it will shift backward directions. So it depends on concentrations. So how it we already discussed. Third, pressure, volume, adding inert gas. So these three depends on number of moles. So if number of moles is same, on that case, if number of moles in product and reactants same, then no effect happen. And pipe, and if not same, then we know that if pressure is decreasing, then it will shift towards more number of moles, and if volume is increasing, it shifts towards more number of moles. And volume and adding inert gas is same, so whatever the effect is happening, adding inert gas also same things will happen. And third is fifth is temperature. So if you increase the temperature, then it will use the temperature and it will shift towards the directions where heat is consumed. So these are the 5 ways we can disturb the equilibriums, and if you disturb the equilibrium, then equilibrium wants to undo that changes. So it will, if you add, then equilibrium wants to remove. If you increase, then equilibrium wants to decrease. So we will solve some related examples. So in which of the following reactions increasing in the pressure at constant temperature does not affect the moles at equilibrium? So it says, in which of the following reactions increasing in pressure at constant temperature? So temperature is says constant. And in which of the following reactions increasing in pressure that will does not affect the moles of equilibrium? So it says pressure, volume, and adding inert gas. This depend on number of moles. If number of moles both in reactants and products, then no effect. If number of moles in reactants equal to number of moles in product, then no effect due to pressure, volume, and inert gas. So where number of moles in both product and reactants are same, there if you increase or decrease pressure, there will be no effect. So here how many moles? 2. Here that is 4. So here there will be effect. So if you increase pressure, if we, for this case, if you increase the pressure, then it will shift backward directions. So this will get affected. So it asks that in which of the following reaction increasing in the pressure at constant temperature does not affect the moles of equilibrium? So where the number of moles in both product and reactants are same, that will not affect. So here how many? 2.5. Here 1. So not. Here not. So here this side 2, this side 2. So this does not affect it if you increase pressure or decrease pressure. This example, this is a very good example. So what it says that PCl pipe going to give PCl3 plus Cl2. So in a closed container at equilibrium, if P of all gases equal to 1 atm. If P of all gases is 1 atm, so T equal to equilibrium, P of all gases is 1 atm, so 1 1. If P is reduced to 1 by 3, then calculate P of gas at new equilibrium and ratio of Pt. So P is inversely proportional to volume. So if P is decreasing, then B is increasing. So what it says that volume is decreases volume if B is reduced to 1 by 3. If volume is reduced to 1 by 3, then pressure is increasing by the same 3P. So if P of all gases is 1 atm, if P is reduced to 1 by 3, then P is increasing by 3 atm, 3 atm. Then what he asks, calculate P of all gases at new equilibrium. So for this case, total pressure is 3. This is T equilibrium, and we want to calculate T equal to equilibrium new, T new equilibrium. For this case, what is happening? So we know that so here basically what is happening, the pressure is increasing, volume is decreasing, volume is reduced to 1 by 3, so pressure is increasing, that is 3 by P, 3P means triple has increased. Okay, so we know that if pressure increases, then equilibrium will shift towards less number of moles, equilibrium will shift. So here how many moles? 3. Here this is 1, this is 1. So here how many moles? 1. Here 1 plus 1, here 2 moles. So equilibrium will shift towards backward directions. Equilibrium will shift towards backward direction. Suppose here 3 minus alpha, then it is also 3 minus alpha, and here, so this is shifting towards backward direction. So here alpha H from 1 mole, alpha H consumed. So from 1 mole alpha H consumed, because equilibrium is, because reaction is happening from towards backward direction. So this will become 3 plus alpha. Okay, because pressure is increasing, then if pressure increases, then equilibrium will shift towards less number of moles. The less number of moles is in the reactant side. So the reaction is shifting in the backward directions. And we know that past this is 3 3 is present. So reaction is, since reaction is shifting towards backward direction, so here is alpha is consuming, and here is forming, because reaction is happening from towards backward directions. So Kp is, this is already in pressure form, so we will directly put, but Kp case we use the normal cases, that is here this is the product, this is P reactant. So product is PCl3 for, this is for actually you are studying the equilibrium cases, this is shifting backward directions. But whenever you are writing the expressions for Kp, we will assume this is product and this is reactants. So Kp is PCl3 how much? 3 minus alpha, and Cl2 3 minus alpha, and PCl5 is 3 plus alpha. Then what will happen? Kp equal to 3 alpha, that is 3 minus alpha square, and this is 3 plus alpha, and taken as Kp is equal to 1. So 3 minus alpha square 3 plus alpha equal to 1. Then we can say 3 minus alpha square equal to 3 plus alpha, and this is 9 plus alpha square minus 6 alpha equal to 3 plus alpha. So if you take this, then alpha square 3 minus, that is 6 alpha, that will this minus, that will minus 7 alpha, and 3, that is plus 6 equal to 0. For this guys, we have to do like you know that whenever ax square plus bx plus c, and if for that you are still using minus b plus minus b square minus 4ac divided by 2a. So here if you say this is ax square plus bx plus c equal to 0, so b is minus 7, so minus minus get plus, so 7 plus minus, and b is 7, so b is 7, so that is 49, and for a is how much, nothing is there, so 1, and c is 6, that is 24, and divided by 2a, a is 1, so it is 2. What happened then? 7 plus minus, that is 49 by 24, that is 25, whole root divided by 2a, that is 7 plus minus 5 by 2a. A is 1, so 2. So x here, suppose for this case alpha is how much? So if you're taking as negative, then 7 minus 5 divided by 2, that is 2 by 2, that is 1. And if you're taking the positive terms, then 7 plus 5 divided by 2, that is 12 by 2, that is equal to 6. So any one value you have to take. So if you take the 1, the 3 minus alpha, the 3 minus 1, that is 2. And if you take the 6, then this will come to us minus 3. So which is actually not acceptable. So we will take alpha equal to 1. So 3 minus alpha, alpha is 1, so 2, 3 minus alpha, that is 3 minus 1, that is equal to 2, and 3 plus alpha, 3 plus 1, that is equal to 4. So here p total equal to how much? 2 to power 8. So they ask that calculate p. Actually you are taking as p, but they say this you have to take as p. So actually they ask in term of p, so we actually calculate by at alpha. So here p and alpha equal to same. So p is equal to 2. So p equal to 1, and ask that ratio between they ask calculate p of each of gas at new equilibrium and ratio of pt. So previously pt was 3, total pressure is 1, 2, 3. T equal to past equilibrium, total pressure is 3, and t new equilibrium, how many pressure? 4, 2, 2. So 2 to power 8. So the ratio between PTs are new each or old one each, old PT by new PT. So old PT is 3, new PT is 8. So this is the ratio, that is 3:8. So P equal to 1, and ratio is PT ratio is 3:8. So next questions here, given that SO2 Cl2 gas is going to convert SO2 gas plus Cl2 gas is attained at 25 degrees centigrade in a closed container. An inert gas helium is introduced at a constant pressure. Which of the following statement are correct? So what is saying that inert gas is adding at constant pressure. So if inert gas it is adding at constant volume, then there will be no effect, because inert gas only helps to increase the volume, and if they assume as constant, then there will be no effect. So they say that inert gas is there adding at constant pressure. So for this case, volume will increase. If inert gas is adding inert gas means volume is increase of mixture. So if volume is increases, then equilibrium will shift towards more number of moles. So equilibrium shift towards more number of moles. So here how many moles? 1. Here 1 plus 1, that is equal to 2 number of moles. So this will happening forward shifts. So forward shifts occur. So where forward shift? So what this says, in a closed container and an inert gas, helium is introduced at a constant pressure. Which of the following statements is correct? So this is forward shift is occurring. So more chlorine is poured. First, concentrations of SO2 and Cl2 and SOCl2 do not change. No, because here is 1, here is 2. So delta Ng is not equal to 0. So if you add the inert gas, there will be changes occur. So more chlorine is formed. Yes, chlorine is in product side, and equilibrium is also shifting towards product side. So more chlorine is formed. B is correct. Let's see concentration of SO2 is reduced. SO2 is in product side. So forward shift is occurring. So it will increases. But here says the reduced. So wrong. So more SO2Cl2 is formed. SO2Cl2 is in reactant side, but it is shifting towards product side. So this will be reduced, not increase. So option B is correct. For this example, what it says, for the reaction CO gas plus H2O gas is going to convert CO2 gas plus H2 gas. Okay. At a given temperature, the equilibrium amount of CO2 can be increased by. So they wants to increase the equilibrium amount of CO2. Okay, they wants to increase this. CO2 they wants to increase. Then how can increase? Here see delta Ng is 0. Here is 2 moles. Here is also 2 moles. So if delta Ng is 0, then P inert gas, P means pressure, B means volume. There will have no effect. So adding a suitable catalyst has no effect. Adding inert gas, no. Decreasing volume, no. So they increase the amount of CO, yes. If they increase the concentration, then forward shifts occur. Decrease the concentration, forward shifts occur. So increase the amount of CO. For this reaction, 3x gas plus y gas x3 y gas. So for this, the equilibrium is affected by. So see here number of moles is 4. Here number of moles is 1. So delta Ng is not 0 here. So this can be affected by temperature. Yes, temperature is get affected. So pressure, yes, because delta Ng not 0, so pressure also has role. Temperature only, no, pressure also has role. So temperature and pressure and catalyst has no role. So catalyst increases both forward and backward reactions. Catalyst increase both forward and both backward. So both backward and both forward. So catalyst has no effect. So pressures only, no. So temperature and pressure. Option A is correct. This example, volume of a closed reactions, the volume of a closed reactions vessel is half. So volume is decreasing, in which the equilibrium this exists now. So this is the through SO2 gas plus O2 gas, that is going to convert to SO3 gas. So here delta Ng is not equal to 0 because here is 3, here is 2. So if your volume is decreases, then less number of moles. Equilibrium shift towards less number of moles. So where less number of moles is there, so here 3, here is 2, so forward shifts occur. If volume is decreases, then less number of moles. If volume increases, then more number of moles. Remember, volume increases, more equilibrium shift, more number of moles. Volume decreases, equilibrium shift, less number of moles. But for pressure case, pressure increases, then less, and pressure decreases, then more. For volume increases, more. Volume decreases, less. For pressure cases, volume increases, less. Pressure decreases, more. So here volume is decreasing, so less number of moles, equilibrium will shift. So here is 3, here is 2. So volume is decreasing. The volume of closed vessel is getting halved, so this will shift forward directions. So equilibrium, the rate of forward and backward reactions will remain same now. Equilibrium will not shift now. Equilibrium shift to the right. Yes, wrong. So option C is correct. This example, in which of the following reactions increasing in the pressure at constant temperature does not affect the moles of equilibrium? I think this we have studied. So if delta Ng is 0, then pressure, volume, or adding inert gas will have no effect. So the increase in pressure at constant temperature does not affect. So if you increase the pressure, it has no effect. So here both side 2, here also 2. So it will no affect. This will get affected, this will get affected, this will get affected. This is another example. Okay, so CO gas plus H2O gas is going to convert CO2 gas plus H2 gas. So at a given temperature, the equilibrium amount of CO can be, so CO2 they wants to increase. So how can be increases? So both sides, here delta Ng is 0, here is 2, here is also 2. So delta Ng is 0. So it can be increased by suitable catalyst has no effect. Adding inert gas, no, because if delta Ng is 0, then P B adding inert gas have no role. So adding inert gas, no. Decreasing the volume of container, no. So increasing the amount of CO, yes. If concentration of CO is increases, so for decreasing the concentration of CO, forward shifts occur. So if forward shift occur, then more CO2 will be produced. So CO2 can be increased. Option D. Last problems. What is says the conditions are favorable for the formation of SO3 gas. So 2SO2 gas plus O2 gas to give 2SO3 gas. So what happened? The favorable conditions for formation of SO3. So they wants to increase the SO3 gas. So what they will do? First check delta Ng. Here that is 3. Here 2. So 3 minus 2, that is equal to 1. So pressure, volume, and adding inert gas we can do. They have rule. Okay. So what will happen is, so we want to increase the SO3 gas. So what we'll do that, and see delta H is negative, they given, means this is exothermic reactions. And if exothermic reaction means 2SO2 gas this means 2SO2 gas plus O2 gas 2SO3 gas. Exothermic means heat is releasing, that is mentioned there. So 198 Kelvin. So what will happen? So this will get this temperature, use this temperature or consume this temperature, and it will do backward shifts. So backward shifts will occur, and but we want the SO3 gas, so we do not want to do backward shift. So the temperature has to be very low. So we don't want this temperature. If we give the temperature, then it will do backward shifts. But we want the more SO3 gas. So we want to decrease this heat. So very low temperature. So need low temperature. So where low temperature, okay, this can be right. Low temperature, okay, this can be right. Any value of T and P, no. High temperature, no. Next. So for pressure, we have to check number of moles. So here how many moles? 2. Here how many moles? 3. So if P increases, then less number of moles. So less number of moles is in product sides. So forward shifts occur. So P increases means high pressure. So option A is correct. Option C is wrong. So option A is correct. Okay, today up to this. Thank you.